Hey everyone, so today we're going to do factorial ANOVAs. These are basically one step beyond the ANOVAs that we did last time. So we're still doing an analysis of variance, and if you remember last week's ANOVAs, we had one independent variable that was categorical, nominal if we're using the formal term, and it has at least two levels. It doesn't make any sense if there's just one. In this case, we have one or more independent variables. So we can actually look at multiple independent variables, how they affect our dependent variable, which is going to be essentially a number, either interval or ratio valued. And we can look at each one of those independent variables by itself, and then we can also look at what happens when those independent variables are interacting with each other, and if that has an impact on the dependent variable. Our dependent variable is an interval or a ratio. It's essentially a number that we're going to work with. So what we're going to talk through here is basically an example. We're not going to actually use any data, though we'll see the results of doing a data analysis on it. And this is to just get a handle on all the different pieces that we'll be looking at. We'll then jump into R and do some real examples, looking at some data that's provided from some tutorials, and also looking at how to visualize some of that. So let's start off with the example. Here we're going to look at this problem from a real research paper that asks, why do older people not remember things as well as younger people? And then it sort of has this sub-question, do they fail to process information as deeply? Is that what affects their memory? And so we put together an experimental design that looks kind of like this. We have young people and old people here, and then we have what we call the condition, which is reflective of the way they process information. So counting or rhyming is really high level, but looking at things like imagery and adjectives, this is kind of deeper level processing. For each of these categories, each of these boxes, we're going to have 10 people input their data. So we'll have an old person do counting, an older person do rhyming, a young person do adjectives, a young person do imagery, and so on. So these are essentially different experiments or exercises that they're asked to do, and we're going to measure how well they perform on them. So you can imagine we've gone out, we've collected all that data, and then we want to actually analyze it and see if there's an effect. So one thing that we want to ask is whether the effects of one independent variable depend on the level, that's the category, of another independent variable. So in this case, we first want to start off knowing what are the independent and the dependent variables. So in this case, our dependent variables are recall. How well do they remember things? Our independent variables are their age, that can be old or young, and then the condition that they were given, which is counting or rhyming or all those other things that were across the top of the little chart that we just looked at. So once we know our independent and dependent variables, we can state the hypotheses. So we have a couple main effects or main hypotheses. The first is just the effect of age. So does age affect people's ability to recall? Our null hypothesis would be that young and old population means are equal. So if we're measuring how well do they remember, young and old people would remember just as well as one another. Our alternative hypothesis would then be that the means are not equal, that there's a difference based on age. We also have a different main effect based on condition. That's what exercise were they asked to do. So here the null hypothesis would be it doesn't matter what they're asked to do, all the populations are equal, so it doesn't matter if you're doing a rhyming exercise or an imagery exercise, it's not going to have any impact on how well you remember things. And the alternative hypothesis is that at least one condition population mean is not equal. Now notice here that when we're talking about condition, we're not separating people out by age. We're just going to look at all the people who did rhyming versus all the people who did adjectives versus all the people who did imagery, and just see, is there a difference in condition that tells us how well people remember things. But then we also want to look at the interaction of age with condition. So our null hypothesis would be that the difference between old and young population means are equal across the conditions. So here we're putting the two together, age crossed with condition. The alternative hypothesis would be that there's at least one difference between old and young means across conditions. So we're actually looking at the combination, which means there's a whole bunch of things that we actually have to compare. So you can do this in R. We're going to do it with a simpler example that we have data provided for. But if you run it, you get a table very similar to the one that we saw last week. So we look at age. Our degrees of freedom are 1 because we have 2 possible ages, just old and young, and 2 minus 1 gives us 1. And then we get our sum of squares and so on. But what we really care about is the p-value here. So this is saying that there is a difference in how well people remember things just based on their age. Our second column here for conditions says that there is a difference based on conditions. So depending on which exercise people do, they'll remember things differently. And if you combine age and condition together, and so we're looking here at does the age impact how well people do on various conditions, we also get a significant result. And we can graph that out and kind of see it. So here we have the different conditions on the bottom. These are error bars, and we're going to look at how to visualize those today. And so what we can see is that certainly for some of these, age matters. For example, here on intentional, we have a really big difference. Young people have much better recall than old people. We can see it here on imagery and here on adjectives too. And there's small differences, but maybe not significant ones on these conditions here. So that's just comparing age within any individual condition. We can also see that the conditions themselves have big difference. For example, people recall things much better if they're doing intentional or imagery or adjective than they do if they're doing counting or rhyming. So how do we put all of that together? We can compute the effect size. So we have this table here, and you'll get the same kind of outputs that we did before. The overall R squared, which is 0.73, that means 73% of the total variance is explained. We can look at age and condition and age times condition, and that gives us an R squared, something similar to an R squared called an eta squared for each of those different variables. I'm sorry, for each of those different factors. And so if we put that all together, what we find out from this analysis is the main effect of age, the main effect of condition, and the interaction between age and condition. And what we actually saw here when we looked into the data, when we visualized it, is that older people were worse at recalling words when they're asked to use those more deeper processing techniques like intentional and imagery. And it supported the idea that older people might lose their memory because they fail to process information as deeply. Now that's an analysis that these researchers found that looks beyond just the simple statistics that we got here. But that comes from the paper that we're basing this data on. And using our R squared, the total variance that's explained by this analysis is 73%, which is pretty good. So that's the main idea that I want you to get of this. The really high level factorial ANOVA is that you can have nominal data, so you have categories for your independent variables, and there can be interactions between them. Note that if you only have one independent variable, you can just do a chi-squared test, right? So say we're just looking at age. Do old people and young people have different recall? Or does recall vary across those categories? Then you might even do a t-test, but you could do a chi-squared test. If we have multiple of those different categories, then we need to look at the interaction between them, and that's when we get into the space of doing an ANOVA. So the next thing we're going to do is look at a simpler example with some sample data and actually get in there and do these tests in R. Okay, so here we're looking at the data. This is provided in an R tutorial that I have linked up for you. So you can actually go through and read their narrative and go through their tutorial, but I'm going to go through it with you. So the problem that we're looking at here and that we have the data for is that you can imagine that we have a restaurant that has 3 new menu items, and that's item 1, 2, and 3 that we're looking at here. And they're going to test them out in a couple different restaurants. So they've picked 4 West Coast restaurants to test it out in. And, I'm sorry, 4 East Coast restaurants, that's E for East, and 4 West Coast restaurants. So you can imagine this is like a McDonald's or a Subway, like some kind of franchised restaurant. And so they have randomly picked some of their restaurants from each coast, and they want to see if there's an impact on the sales of this new item. So we have a couple things that we need to compare here. One is there a difference in how well each of the items sell? So does item 1 outperform item 2 or item 3, and so on. We want to see if there's a difference between the coasts, the East Coast and the West Coast. And then we want to see if there's some kind of interaction between that. And what that might mean in this case is that East Coast people have different tastes than West Coast people. So it could be one item sells well on the East Coast, but not as well on the West Coast, or vice versa. And so that's the interaction between the coast feature and the item feature. So we have our data all summarized here. I have this stored as fast food, and then we're going to load that up in R. Okay, so here I am in R, and I'm going to load this data up. So I'll call it df3, just to match with what's in the tutorial. And that's going to be equal to read.csv, file.choose, and header equals true. And then we'll pick our file. So now we've loaded that up. And what we want to do is concatenate the rows into a single vector. And that's going to allow us to do one note to throw in here. The file that you're actually loading up doesn't have the East and West Coasts on it, because that'll screw up our analysis. So I edited this. It looked nicer when we were going through before, but this is what the file you're loading looks like. And so if we take a look at it there, that is everything that should be there. The next thing that we're going to do is take all of the values that we have in here, and instead of leaving them in kind of a grid like this, we're going to put them into a single vector, and then we'll look at how to process that vector. So we're going to put this in a vector called R. Remember, we use the command C to put things in a vector. T is going to flip this around into the right form. And so we say as matrix df3. And so that basically takes this grid of data, it treats it like a matrix, and it's going to transpose it in a way that we get it into our vector. We're going to look at some more examples of this with data formatted differently. So don't worry if you feel like you couldn't maybe reproduce that. Once we've got that, what we can see is that we have our data. Now all of our rows are just strung out into a single vector. What we can do now is list our factors. So we're going to say our first set of factors is item 1, item 2, and item 3. Our second factor is going to be East or West. And then we need to count how many values or levels there are for each factor. So we'll say K1 is the length of F1, and K2 is the length of F2. Now, of course, these are short here, and we could just count that there's 3 or 2 of them. But sometimes you'll have a bunch, which we'll see in future examples, and so length is a good thing to know. The next thing we want to do is know how many observations that we have per treatment. Basically, for each cell in this grid, for item 1 in East Coast and item 2 in West Coast and so on, how many observations do we have? In this case, we have 4, because we have 4 East Coast restaurants serving each item and 4 West Coast serving each item. So we'll say n equals 4. We're going to use these in our future calculations. So the next step is that we're going to make a vector that basically lists out all of our levels and the response and maps them to the response data that we stored in R. So I'm going to use this thing that looks sort of complicated, but you'll see basically it's just going to list our levels. So we use this function GL to generate levels. We're going to say K1, that's how many of them are there. And then we're going to enumerate how many observations we have and say that this is for factor 1. And what this does, oops, I have a typo in there. Sorry, that should be K2. This is correct in the tutorial that I linked to you. What that actually gives us is item 1, item 2, item 3. Item 1, item 2, item 3. It shows us a list of the factor 1 names that map to the responses that we have in that vector R. This is item 1, this is for item 2, this is for item 3, and so on. We're going to do the same thing for factor number 2. We're going to generate the levels. Here's how many of them there are. Here's how many observations we have for the first level. Here's how many total observations we have. And we want to list this out for factor 2. And you can see that it has a bunch of easts and a bunch of wests because that's how our data is broken down. We have all the East Coast data first and then all the West Coast data. Once we have this, we can actually do our analysis of variance. So I'm going to store it in AV, and then we'll do an analysis of variance. We're going to take our observed data and look at that in these two factors. And if we get the summary for that, all right, what do we see here? So we can see, let's spread that out a little bit more and try it again. Okay, so for TM1, we get this 0.15, which means that there is a significant difference in our first factor, which is the different items. And we have a very significant difference in TM2, our second factor, the East Coast and the West Coast. So the coasts did see differences in sales. And then in the combination, we also see a significant difference, though not as big as the other two. And what that means is that there's some interaction between the two factors, so between the coasts and the items served. So it means that East Coast people have differences in which items they buy compared to West Coast people. And so we see 3 different significant effects here. Now we're going to look at how to do this in a slightly different way. We have a way bigger data set. All the R commands in this data is also available on the website for you. And we're just going to look at another way of doing a similar kind of analysis. So here we have restaurant data. The place ID is just giving us basically an identifier for the restaurant, and we have a whole bunch of different variables here. Rating, the food rating, the service rating, the name of the place, address, and so on. And we're interested in some of these factors over here. Do they serve alcohol? Is there a smoking area? Is there a dress code? So we're going to start by actually looking at the dress code and the rating and see if the rating varies based on the dress code. Now this is going to be a more straightforward analysis of variance, and we'll eventually get in and look at some other things. But let's just start off with that. So we're going to do an analysis of variance, seeing if the rating for the restaurant varies based on the dress code. So we're going to go back into R. We're going to load up this data. I'm going to store it in D, and that will be the things that we've been doing all semester. File.choose. Oh, picked the wrong file there. Okay, so now we have our data loaded, and what we're going to do now is compute a whole bunch of different statistics based on the level. So the levels that we're interested in here are the dress code. If we just do $$ dress code, we get the whole list of them, but we can see there's casual, informal, and formal. What we want to do is we're actually going to step through all of the things that we'd look through in an ANOVA here, and we're also going to see how to plot it. So we want to get the mean for each of the different dress codes, the standard deviation, the number of observations for each of the dress codes, the degrees of freedom, and then we're going to use that to compute critical values that will allow us to get confidence intervals. And we'll talk about what all that means as we do it. But first, we're going to look at a new function called tapply. And so basically, you can see that this is going to apply a function over an array. So we can give it a list of stuff, and it's going to apply a function to that. Let's see how that actually works here. So I'm going to create a variable, my means, and that's going to be equal to tapply. So we're going to apply the function. First, we're going to ask what we want it applied to. So we're going to apply, in this case, the mean is the function we'll be doing. So we're going to apply the rating. We're going to group that by the dress code, and then we give the function we want to apply, the mean. And if we look at the output of that, we can see we get the mean rating for each of the different dress codes. Okay, so this is the thing we're applying the function to. This is how we're going to group it, and then this is the actual function. So we're going to do the same thing for standard deviation. I'll call it my standard deviations. That will be tapply, exactly the same. The standard deviation of the rating, grouped by the dress code, and I'm going to use the SD function. We're going to do, I'll call it my ends. That's going to store how many observations are there. Again, tapply. I'm actually just going to copy and paste this. And then we'll use length, which we saw before. That'll actually count how many observations there are. The degrees of freedom is really simple. It's just the number of observations minus 1. And then we need to get the critical values. So what we mean by that is that in this case, we're going to construct a 95% confidence interval. These are going to be little bars around the mean that show where 95% of the values will fall. And so basically we want that to go up to 95% on either level. That means that we're going to have 2.5% above that's left out and 2.5% below that's left out. And so to do that, I'm going to store this in a variable called that I'm going to call tcrits for critical values. And we use this function qt. So qt actually does the t distribution around our data. And so we're going to do qt, we'll say 0.025. So we're going to leave off 2.5%. It's a 95% confidence interval, so we'll have 2.5% on either side. So we're going to say I want 2.5% left off, give it our degrees of freedom, lower dot tail equals false. So we have 3 values here. This is the range around the mean for each of these different values that we're going to look at. And it knows to do 3 of them because we gave it the degrees of freedom, and the degrees of freedom we computed here, my ends minus 1, but my ends actually has 3 values, right? It's the number of observations that we made for each of the different dress codes. And so we have a different number of observations for each dress code, and that's why we get a different range around each one of these that we use for our confidence interval. Okay, so now I want to get the standard error for our distribution. So I'm going to call that SES will be my SD, so my standard deviations divided by the square root of n for each one of those. And now I can use that to create confidence intervals, upper and lower levels. And I do that by looking at the mean and then looking at how far above the mean do I have to go and how far below the mean. So we've got the actual means stored, and we know this is giving us our range here in our critical values, and we multiply that times the standard error to actually see how many steps above and below do we go. So for the confidence upper limits, I'm going to take my means and I'm going to add on how far above we would go to capture that confidence interval. So I'm going to take the critical value times the standard error that we would expect. For the lower end, which I'll call confidence interval CI dot lower, I'm going to do the same thing and just subtract it. So I'm going to go below the mean, the amount that is specified by what we've calculated here. Okay, and now I actually want to pull this all together and plot it. So we're going to take the big confidence interval is data.frame, which groups all of our data together. We'll say dress code equals the levels of our $ dress code the rating we want is stored in my means. And then I'm going to give, it actually asks for confidence interval dot upper, and I'm just going to set that equal to the confidence interval dot upper that I've already computed. Oops, I hit enter too early. We need to do the same thing for CI dot lower, and I'll set that equal to what I've already computed. No, I have another typo in there. Okay, and so now we actually want to plot this. So to do this, you need to make sure that you have plotting software installed. I had to do that at the beginning, so let's take a look at this. We're going to go to Packages. You want to see if you have ggplot2. If you don't, click on Install, and you'll find ggplot2 there. Click it and install it. I've already done that, so I'm going to hit Cancel. Once it goes through the whole process of installing, make sure you come back to Packages and check it so it's on. If you don't check it, it won't work. And that's going to give you access to the ggplot functions, which are really powerful plotting devices. So in this case, we're going to do ggplot, and we'll do r.ci, what we just computed there. That gives us the confidence intervals. And then to specify our axes, we'll do AES, and then parentheses, X is dress code, and Y is rating. And that gives us nothing exciting because we have to add some other features in there. So I just hit up to get the same commands back, and we're going to add in a few more things. We're going to do plus GEOM underscore bar stat equals identity, and then plus, so this GEOM is a package that allows us to draw things, basically. And we'll draw in error bars. And we're going to give that a few more features. AES. So Ymin will be our confidence interval lower. Ymax will be our confidence interval upper. And then we'll say width equals 0.2. And now we get this beautiful chart. do not try to type what I just typed by reading off the screen. Load up the R file that's linked up with the lecture today, and you'll see the full command there. You can copy and paste it. You can try to type it in, but it'll be easier like having the actual text in front of you as opposed to trying to read that off the video. This is not the kind of thing I expect you to have memorized. If you do get deep into plotting and drawing graphs in R, which some people do, you'll become more comfortable with this. But what you basically want to know here is that it's plotting our data, and we've told it what the bars should look like and what the confidence intervals should look like. And these little bars sitting on here, these are the confidence intervals. So the big bar just goes up to the level of the mean, and then the confidence intervals show where we would expect 95% of the values to fall. So that gives us a good sense of what's going on because it allows us to see, for example, the mean of the formal dress, the mean rating there, is above the highest value that we would expect in the 95% confidence interval for casual and similarly for informal. And so that suggests that there might be a really significant difference. Now we actually want to do the analysis of variance. So all that stuff we were doing was for the plotting. Now we actually want to do the analysis of variance. So I'm going to do it all in one command. We're going to ask for a summary of the analysis of variance, where the rating is dependent on the dress code. We'll say data equals D, which we've loaded up, and here we get our results. Let me run those again just so they're spaced out right. Okay, so we can see that there is a significant difference. It's significant with 2 stars here, so our p-value is less than 0.01, and we get our residuals. So that's good, and we can actually do some comparisons then. So we can try doing pairwise t-tests, and we're going to compare the rating to the dress code. And because there's only 3 tests here, we're not going to do any adjustments. So we'll do P ADJ equals none. Here's our pairwise t-tests. So what those tell us is that there are significant difference between formal and casual, between formal and informal, but not between casual and informal, which is very much in line with what we see in the plot over here, that formal is significantly higher, but we don't see any difference between our end ones for casual and informal. Okay, so now that was just a standard ANOVA that we did. That wasn't actually getting into the factorial ANOVA that we were doing today. And the first example that we looked at showed a really complicated way to do that, where we took this data file, transformed it into a vector, and showed some ways to lay out the factors and break up our vector. And you may sometimes end up with data that looks like that. Here we've loaded up our data into a table form, and so we can actually do it in a much more straightforward way. So remember that we're looking at restaurant data. Let's come back here and just look at it again. And so we have a few different ratings: the overall, the food rating, the service rating. And then we have a bunch of attributes of the restaurant themselves. So for example, we have area. Is it open or closed? So that refers to the floor plan. Is it an open floor plan or a closed floor plan? We also have alcohol. Do they serve alcohol or not? And so we might want to know, does the service rating, is that impacted by whether or not they serve alcohol? Is it affected by whether they have an open or a closed floor plan? And is there any interaction? And so to do that, we're going to do an analysis of variance, a factorial analysis of variance, because we want to see, 1, does alcohol have an effect? 2, does the floor plan? And then is there any interaction between those two? So maybe do people who are drinking prefer an open floor plan versus people who are not drinking prefer a closed floor plan, for example. So we'll store that in a variable called AV. We're going to do an analysis of variance, and we're going to really simply just ask if the rating depends on area times alcohol. Data equals D, and that's it. So we can do a summary of that analysis of variance. And here we don't see any significant results. Let's try the same test, and I'm going to do it all in one command. Ask for a summary of the analysis of variance of, let's say, the service rating depending on area times alcohol. Data equals D. And here we do see some significant differences. Not really in any of the two. So there's no significant difference just in the area. And there's no significant difference in the service rating just based on whether they serve alcohol. But there is a significant difference if you put them together. Okay, so let's actually take a look at how to plot this and then we'll be done. So we're going to do ggplot again. D is going to be our data source. And for our axes, X will be alcohol, Y will be service rating, and then we're going to do fill equals area to say that we're filling this in. And then we'll do a plus on that, stat summary, and this is just going to add in some features for the graph to have. So we'll say fun.y equals mean. So that's the function that we're going to use on the y-axis, the service rating. We're going to do the mean. Geom equals bar. So we're going to look at the geometry of this will be a bar graph. And position is dodge, just to make it look nice. And here's the graph that we get from that. Kind of some like 80s Florida colors. But so we can see the categories for alcohol down here. Full bar, no alcohol served, and wine and beer. And then the area is actually plotted as the bar. The service rating is on the y-axis. So for a full bar, a closed area does not do as well as an open area. For wine and beer, the same is true, but that's probably not significantly different. We'd have to do some pairwise t-tests. And if there's no alcohol, a closed area does much better than an open area. So that allows us to see that if we're just looking across alcohol, doesn't matter. If we're just looking across the area, it doesn't matter. But when you put the two together, you start to see big differences where depending on the type of alcohol served, the area really matters. And so that's what we can get with these factorial ANOVAs. You have multiple categories, multiple independent variables that have different levels, and you can compare the means of a certain value within there. So it's just extending beyond what we were able to do last time. Last time we had nominal independent variables, but we had one and we were comparing the means. Here we have multiples and we can look at the interactions.